Okay. So right now I can see only 33 students here. So I'm going to start this class with there are two different slides. Let us go with that. Is the screen visible? Can I get one feedback?
Yes, sir.
Okay, so I will be using some slides here. So in the meantime, suppose if anything lags behind or if you couldn't see, so feel free to stop me and remind me. Okay. I mean, if there is any technical issue, let me know that. Okay, so you're free to stop me and tell me about that. Okay, so this is a very entirely a new topic that you are now encountering because just like atomic absorption spectroscopy was also a new one. So I am dealing with the analytical chemistry in your fifth semester here. Okay, so we have seen already atomic absorption spectroscopy by using atomic absorption spectrometer. So which is one of the instrumental method of analysis that helped in analyzing various metal atoms present in different kinds of samples. Okay, so this that was an analytical tool. So that helps in the analysis. Okay, and to continue with that, here is another method. So which has even other different type of it works in a different principle and even the applications are different. Okay, so this also the common thing is this also an instrumental method of analysis. Okay, so this analysis is achieved by a very customized equipment. Okay, so actually what is mentioned in your syllabus is a thermogravimetric analysis. Okay, so here you need to remember gravimetry. Okay, gravimetry is what you have learned in theory as well as you are experiencing in the lab sessions. And so, but this is little different here. The thermogravimetric analysis is a bit a different one. And there are several types of thermal analysis. Now, what I'm speaking is a broader term that is called thermal analysis. And our thermogravimetric analysis is just a one part of it. Okay. So I just tell you what is meant by thermal analysis, and then we get into and then we confine ourselves to our syllabus boundary that is on thermogravimetric analysis. Fine, what is meant by thermal analysis? If you ask, it is something like when you heat a substance. It is you can't say it is entirely belongs to chemistry only. So you can say this is part of the material science. Okay, if you want to study a material for various properties of a material, so then thermal analysis is a very important analytical tool. So that helps in understanding a new material. So any material scientist, so he will look for the better equipped thermal analytical tools for his research work. Okay. So it is, as I told, it's a branch of material science where the properties of materials are studied as they change with the temperature. So very simple one. The definition looks very, very simple. It is a branch of material science where the properties of materials are studied as they change with the temperature. Okay. Several methods are commonly used, and these are distinguished from one another by the property which is being measured. So I mean to say, when you put any material into flame, okay, so many things will happen. Apart from simply if it is having a fuel value, it can catch fire and it can undergo combustion. If it is not even if it is not a fuel, or it is not having any fuel content, but yet there undergoes various changes in its physical as well as chemical properties. And if you are focusing on any particular property of the material which changes with respect to the temperature, okay, so and if you study that in general can be called as a thermal analysis. Okay, and depending on, as I told, depending on the property which is being measured, or which is being measured with respect to change in temperature, so there are different several types of thermal methods of analysis. Now we can just look at the several abbreviations that are here. Okay, so that are been used. I think better let me go with this one. Now these are the different thermal analysis. Okay, so dielectric thermal analysis, called as a DEA. So what it measures is a dielectric permittivity and loss factor of a material when studied with respect to temperature. And then DTA, differential thermal analysis. Okay, so when a temperature difference with respect to a standard reference is being done, so that is called differential thermal analysis. And then differential scanning calorimetry. When you study instead of temperature, the heat difference. So I hope you understand what is the difference between temperature and heat. Okay, so if you focus on heat difference, then it is called differential scanning calorimetry. And then dilatometry. Okay, so this is the change in the volume of a material when you put it into flame or a temperature, or when you put in a temperature studies. All right, and dynamic mechanical analysis, DMA. This is a mechanical stiffness and dampening property of a material with respect to temperature. And then evolved gas analysis, in short form EGA, stands for gaseous decomposition products analysis. Okay, with respect to everything is with respect to temperature. Then laser flash analysis, thermal diffusivity and thermal conductivity. And then thermogravimetric analysis and thermomechanical analysis, TME, is the dimensional changes. And thermo-optical analysis, optical properties. That means when you heat a material, what happens to its optical property? So you can't, I hope you would have not imagined. So these many changes will happen when a material is just heated. Okay, so that's what the material science is, a very big branch of science, wherein there is an endless scope for the new research. So after doing BSc, and if you would like to pursue masters in chemistry or allied fields, and then you have a good scope of doing PhD in the field of material science, which will never stop, because there is a quest for human to look for new material for his new desires and new for new applications and for new utilities. So this branch is a evergreen one, so which you can think for opting for your research. Fine. So there are various, I just have mentioned, there are, I am not going in very detail with the other aspects here. Okay, so, but however, I should mention that in the earlier semesters, like your seniors, have studied differential thermal analysis and differential scanning calorimetry, okay, along with TGA and DTG. So the four techniques were mentioned to them, and I took classes on those things earlier. But for you, it is only mentioned, you are only confined to this one, thermogravimetric analysis. Okay, no other techniques are being mentioned. Fine, I can say just there is an introduction to a few people to this thermal method of analysis, and then out of interest you can learn, and or maybe in the higher level you can go through these other techniques. Okay. So then, what is thermogravimetric analysis? That is what we are going to look at. Again, here is another slide wherein you can see the method, the abbreviation, and then the property measured. Okay, so I again try to just go through this again. So this is DTA, differential thermal analysis. What we do is temperature difference. And here DSC, enthalpy change. Enthalpy means heat. Okay, TGA, what we are now focusing will be change in the mass with respect to temperature. Means when there is a heating program, I use the term called heating program. I just unlearn the idea later. So when you heat a material, so is there any mass loss? Okay, that is what we studied in the thermogravimetric analysis. And in case of DMA, there is a deformation study, and even in dielectric thermal analysis also there's a deformation studies. And then EGA is a evolved gas analysis. So when you heat a material, if some gases are evolved, and if you study the gas that is being evolved, that is called the evolved gas analysis. So wherein you will be the gaseous decomposition, so is being studied with various techniques. And thermo-optical analysis, you are going to study the optical properties of various materials. So thermal analysis is defined as series of techniques for measuring the temperature dependency of a physical property of a certain substance while varying the temperature of a substance according to a specific program. Program here means the heating program. Okay, so the physical properties include mass, temperature, enthalpy, dimension, dynamic properties. Okay, and the even other several various other properties. So conventionally, thermal analysis has been mainly employed in measurements for research and development, but in recent times it is used in many practical applications as the testing standards on the basis of thermal analysis. They have been established for example, in quality control in the production field, process control, material acceptance inspections. So these are the various wings with which these thermal analytical method procedures are being used. It's also applied in wide fields like polymer industry, glass industry, ceramic, metals, explosives, semiconductors, medicines, and foods. So you can just imagine the versatility of this particular technique. So thermal analysis is an entry-level chemist or a new function for the experienced pharmaceutical scientist. So it finds a varied application in the pharmaceutical industry. All right, so this is actually I would like to skip this particular slide because so it contains nearly 200 slides and it goes beyond your syllabus boundary. So that's how I would like to go over with another slide here. And as I told, I am going to complete this part of the your studies like syllabus of thermogravimetric analysis in today's class. Yeah, now I am just taking out another slide here. I hope this is visible. If not, you can just tell me. So here we are looking at some definitions of thermal analysis, thermogrammetric analysis. Okay, and we'll be focusing on TGA and DTA. Okay. Sorry, not DTA. I'll be talking about DTG. So as again, maybe a repetition. So it is a TA stands for thermal analysis. Is a group of techniques that study the property of materials as they change with temperature. Okay, so it may be a repetition, but still I do this because so as the concept is new, we should be you should be easily get into this one. Okay. In practice, thermoanalysis gives properties like enthalpy, thermal capacity, mass changes, and the coefficient of heat expansion. All these things will happen. So solid state chemistry uses thermal analysis for studying reactions in solid state. Look at this. This is again a very new topic title. You might have heard of it as solid state chemistry. Solid state chemistry means you can. I just tell you one thing. If you do a reaction normally in our laboratory, when you are doing a reaction is done normally in an in majority of the cases you do it in an aqueous medium, and in other cases we'll do it in an organic liquid or a solvent. But overall, we do a reaction in a liquid solution. Okay, we dissolve the reagents, we dissolve the substance, a solid material, and then carry out, because in the liquid phase, the reaction rate we think is good. There is a good collision between the reactants and you will get a product. But however, there is a new branch of chemistry that has been evolved called as a solid state chemistry, wherein you're not adding any solvent at all. Okay, we are simply mixing two you know, the solid components or the reagents, they're just thoroughly mixed and you're going to get a product. So that technique or that new type is called solid state chemistry. So wherein such branch will use the thermal analysis for studying the reactions in the solid state. Okay, so thermal degradation, reactions, and phase transition and phase diagrams, all these things can be considered there. Okay, so these things I told in that slide, and let me proceed further. This is how it looks like the TGA instrument. I tell you, this is a picture of this TGA instrument with which you cannot understand anything here, but I do explain that in very detailed shortly. Yeah, let us now directly get into thermogrammetric analysis. Okay, so we'll start with your syllabus. Let us confine with ourselves with a syllabus boundary is thermogrammetric analysis. Okay, so if you go by the term here, this is analysis. Okay, you are doing some analysis, and if you ask me what type of analysis you are doing here, so here you do both the qualitative as well as quantitative. Both can be done here. So one can do both qualitative analysis as well as qualitative analysis in this particular technique. And here other terms. So there is a thermo as well as gravimetry or gravimetric is there. So gravity or gravimetry, so it stands for, if anybody asks you what is gravimetric analysis, you know that it is a analysis which is being done or which is done by measuring the weight of the sample. So you just recall you have done the gravimetry of barium, gravimetry of iron and aluminum. Okay, so how did you how did you concluded the final analysis? Is you just prepare, you just the analyte was converted into suitable chemical form by adding certain reagents, and you have precipitated it out and then filtered it out, and that particular precipitate you just have ignited, and finally you just have measured, finally you have measured the weight, and then the final result was calculated based on the weight of the sample finally that you have measured. Okay, so gravimetric analysis in total, it is analysis achieved by taking a weight. So what I said now can be a question in your Viva. Okay, for Viva, practical Viva. Okay, if anybody asks you what is gravimetric analysis, so it is an analysis which is achieved by weighing a sample in a suitable chemical form. Fine. Now, what is achieved? Another thing that is mentioned is a thermogrametric analysis. Okay, so what it means is, so you are going to measure the change in the weight of a sample with respect to a heating program. Okay, a sample, a chemical compound is heated continuously in a TGA instrument. Okay, and that instrument is such that there is a simultaneous or a continuous measuring of the weight of the sample in the due course of heating. So two things are done simultaneously. One thing is the sample is continuously heated. The sample is continuously heated, and while heating, the sample is continuously measured for its weight. The weight of the sample is continuously measured. Okay, so it is correlated in such a way that at any temperature, if there is any weight increase in the weight of the sample or decrease in the weight of the sample, both can be recorded. So that is what the essence of TGA analysis. Okay, so TGA basics, it measures the changes in weight. It measures the changes in weight in relation to changes in the temperature. Okay, so it measures the changes in weight with respect to change in the temperature. The measured weight loss curve gives information on changes in the sample composition. Okay, if there is any change in the weight, I can say change means either increase or decrease. So only two things can happen. And so you can do the study of that study. So if there is any change in the weight of the sample, obviously there is a change in the composition, chemical composition of the material. So that you are going to, that is going to happen. And you can measure thermal stability of a material if no change occurs at a range of temperature. What does it indicate? It indicates there is no the material is stable. So as good as you are just measuring the thermal stability of a material, and then kinetic parameters of a chemical, kinetic parameters for chemical reactions in the sample. Okay. So these things we see shortly. And a derivative weight loss curve can be used to tell the point at which the weight loss is most apparent. Fine. So this is also we are going to study here. Okay, so before I proceed further, I should make you see one particular slide here. So yeah, now this is where I want you to focus, and later we go back and come to this slide again gradually. Okay, now this is just a block diagram which tells you about this particular analysis. Okay, so what does this equipment involve? Now here you can see there is a furnace liner. So here you can see, I hope you can see the cursor movement here. So this is something like a vessel. This is a vessel, right? Actually, this vessel or this entire whatever the things that are here, they are contained in a furnace. Furnace means it is a heating unit. Okay, so the things are heated here. So in a furnace, And actually this is actually a furnace liner, means wherein the heating is done. And here is something a very small cup, okay, in which you can put sample. Now this is the heap of something what you see is nothing but a sample. Okay, now this is a sample container or a cup, sample cup. And here there is something what is called as a thermocouple. Thermocouple is a device which is going to measure the temperature. Okay, the role of thermocouple is to record the temperature, right? And at the same time, so this entire unit is connected to a balance, a chemical balance. Means what? So the balance is such that it is going to measure the weight of the sample continuously. So suppose you have a like a digital balance or a chemical balance, what you have seen in our laboratory. So what do? We just put the sample and measure. Suppose if there is a chemical balance, we put a sample, and on the other pan we put the standard weight and take a measurement. It's not like that, but here this is a balance which is going to measure the weight of the sample continuously with the increasing heat of the with the increasing or with the heating program. Okay, so there are some keywords like we are using the heating program. It is a key term that we normally use in the thermogrammetric analysis. Okay, and thermocouple is the one which is just like actually the furnace will attain the temperature to about 2000 degrees Celsius. Okay, so it is made like that. The heating program can be done like so. For an ideal heating program will be from minus 140 degrees Celsius to 2000 degrees Celsius. Look at the range of temperature. Okay, so and you can imagine the way with which this the equipment is being made. And in both the cases, our normal thermometer, a mercury thermometer, will fail to record the temperature. Okay, so if the temperature goes beyond the boiling point of mercury, then our normal thermometer cannot be used. It cannot be used. So if you look at the thermometers that are used in our laboratory, so which can measure the temperature from a range of minus 10 degrees Celsius to the maximum of 350 degrees Celsius. Okay, so you don't have thermometers beyond that range, so that are normally used in the laboratories. However, if any temperature is to be measured beyond the 500 degrees Celsius or much higher and higher, like 1000, 2000, then the calibrated thermocouple so is being used. This works on the principle of the dimensional changes of a metals. Okay, the thermal expansion of metals. Okay, so that is the actually basis. I'm not going to go over with that in detail. So however, this is being used in recording the temperature, measuring the temperature. And finally, this entire thing is connected to a recorder or a data acquisition unit. Okay, data acquisition unit is just like a the final the readout device, as we have seen in AAS. Okay, now this is what the something phenomenon is happening, heating is happening, and balance is the one which is just like a we can say like a detector compared to that one. Means continuously it is going to measure the thermocouple as well as balance is the detector. You can say the heating program is something, the activity that we do it on the sample, and finally we record all the changes that happens here. Everything is been recorded. Okay, so recorded could be a computer monitor on which a display has been done, or else it could be a piece of paper in which you will get a thermogram. Okay, just like a spectrum. Okay, so what you get, the final reading is recorded as a spectrum. So here what we get is called a thermogram. So I show you how will the thermogram shortly. But however, this is just a block diagram of the various components that are there in a thermogrammetric analysis. And here what we mentioned is a programmer. Programmer means what? Now, as you told, this is here is a sample container and there is a furnace liner. A programmer is the one which will monitor or which will have a control over the heating process. Okay, so like if you want to heat it, then actually the heating is not done by flame here. Okay, so furnace, whenever you come across a term called furnace, there is no flame. The heating is not done by flame. Okay, so this thermal analysis, thermogrametric analysis, we never use flame here. Okay, the heating is electrically done. And your the furnace liner, so that is controlled by a programming device. So wherein you can have a control over this entire unit, so that you can increase the heat or decrease it or make it cold. So all these things are under controller here. That's what the programmer, right? And you can set a heating rate also. Heating rate means, so per degree Celsius, what is the increase in the rate of what is the increase in the degree Celsius of a temperature? Like for example, a heating rate could be 10 degrees Celsius per minute. Okay, that means there is a increasing in 10 degrees Celsius in 1 minute. Okay, so that is what happens. Or you can increase the heating rate to 50 degrees Celsius per minute. Means in 1 minute, so the temperature increases to 50 degrees Celsius. So it all depends on your requirement, and we'll even can change the heating rate of a thermogrametric analysis. Okay. Now let us. I hope you understood this particular picture, in which the core understanding of this analytical technique is there. It's very simple. You are heating a substance. Under your control. Okay, and continuously measuring the weight of the sample. Okay, so anything could happen. Most of the cases there is a weight loss. Weight loss will happen, but in occasionally one or two cases there is a increasing the weight. And finally you'll get a plot, and that plot will tell you a lot of things, lot of information, and that we are going to study. Okay, so far if there is any doubt, I do welcome any of you. If you have any doubt, you are free to stop me and ask. Okay. All right. If no doubts, let me go back to the earlier slides and come back to this one. Okay. So now we have seen this. Okay. The phenomenon causing mass changes in thermogrametric analysis. Okay. So we have seen the basics of this one, and why there is a mass change. So what are the situations in which there is a change in mass with respect to a heating program? See, the mass change can happen for two reasons. One is a physical. There is a change in the some physical parameters, as well as in the chemical parameters. Okay, so both can happen. So gas adsorption. Okay, so if there is any gas if a gas is being adsorbed, then there is a increasing in the increase in the weight, the increase of weight. And if there is a gas desorption, means the adsorbed gas, if it goes away, then there is a weight loss. Okay, and phase transitions. Some phase transitions like it may undergo vaporization. Okay, the substance may undergo vaporization. So vaporization will lose some of the components, and there is a weight loss. And the substance may undergo sublimation. Substance may undergo sublimation, like it can directly convert from solid to the vapor state. So in all these physical changes, so there is a change in the mass of the sample. And what are the other chemical reasons here? So a compound may undergo decomposition with the heating program. Okay, so on heating, compound may it can undergo decomposition. Okay, so and there is a breakdown reaction. There might be some reactions might happen. Okay, so that will lead to the evolution of certain components as a gas. So gaseous reactions. Okay, and chemisorption may happen, right? Adsorption by means of chemical instead of physical forces. So that is also possible. And in some case, in case of decomposition, oxidative decomposition can happen. And in some case, oxidation of a metal oxide formation can have an increasing in the weight of the substance. Okay, so these are the phenomenon that might happen in due course of a heating program. And remember, in the physical state, so physical changes. So one thing is the I can see the melting point. So one cannot determine the melting point in a thermogrametric analysis. Okay, so because during melting, there won't be any change in the mass of a substance. Okay, the mass of the substance remains same. Only thing is there is a phase transition, like it goes from solid to the liquid. Okay, only if there is some any mass loss during the melting point, only that can be recorded. So your instrument records only if there is a mass loss or mass gain, or weight loss or weight gain. Okay, no other things can be recorded. So it is sensitive only to the change in the mass of the substance, change in the weight of the substance during a heating program. Okay. So what are the applications? Applications, of course, we do go with this in very detail shortly, but have a glance. Thermal stability of a material purity can be checked, and determination of humidity. Okay, and you can have an examination of corrosion studies, oxidation or reactions with reactive gases, gasification processes, and kinetic processes. So we see to those things shortly. Okay, now there are if you consider this actually a graph, and this graph is nothing but a thermogram. So the thermogram is a plot of actually this actually change in temperature. Okay, so sorry, it is not a temperature. It should be with the weight loss. Okay, so we see to another thermogram later. But what you can see here is the heating and cooling rate. It varies from 1 to 50 degrees Celsius per minute. And whereas sample size, what is the sample quantity required here? The one thing is sample to be usually sample that is studied in a thermogrammetric analysis are only the solid samples. Okay, because as I told you here, this is having an application in the material science. So most of the things we come across the materials, the solid materials. So it finds application for solid stuff. Okay, and that stuff can be of the size of 1 to 100 milligrams. Okay, typically it can be 5 to 20 milligrams. All right. Now here is an example, like you have a calcium oxalate, CaC2O4 or Ca, what is that? COOH and COOH. Okay, so that is nothing but oxalic acid. This is the oxalate ion, and that is bound to calcium 2 plus, and that gives you calcium oxalate, and actually it forms a monohydrate. Okay, when you heat this material or when you study this material in a thermogrammetric experiment, so initially there is a loss of one water molecule that leads to the formation of anhydrous calcium oxalate. So on further heating, initially there is a this is a loss of water, and here there is a decomposition reaction that leads to the removal of carbon monoxide and leads to the formation of calcium carbonate. And further heating, this calcium carbonate further decomposes to give out carbon dioxide, and you end up with a calcium oxide. And look at these things. So what is evolved is a H2O, and here carbon monoxide, and here carbon dioxide. Okay, and all these materials here, what that finally remains calcium oxide is a very stable metal oxide, okay, which remains as a solid stuff. And some of these gases have been removed, and in due course of each removal of each gases here, there is a weight loss, and that weight loss is recorded in the thermogravimetric experiment. Okay, so calcium oxalate monohydrate, a standard material often used to demonstrate TGA performance, and that exhibits 3 weight losses with respect to temperature in an inert atmosphere of nitrogen. Usually it is carried out in an atmosphere of nitrogen. In a nitrogen atmosphere it has been done. Okay, so now here is the actual thermogram. Okay, now this is the picture of a thermogram in front of you. Here this is a thermogram of a decomposition study of calcium oxalate monohydrate. Okay, so what we have seen earlier, this is 1 second. Okay, so this calcium oxalate monohydrate has been studied for this TGA analysis. Okay, and look at the graph here. Okay, so just look at the graph. On this y-axis, you can see 20, 40, 60, 100, 120 like this. Okay, so not 120. So the actually our graph, it starts from 100 here. Okay, our graph begins from here and then continues like this. What do you mean by that? This is actually percentage weight loss. This is actually the unit here is percentage weight loss. So when you begin with, you will have whatever be the weight of the sample, the instrument is calibrated to set that one. Suppose you take a 20 milligram of a sample of calcium oxalate monohydrate. Then what the instrument does is initially it takes the weight of the sample as 20 milligram, it weighs it. Okay, before you start heating, it takes the weight of the sample, and instrument get itself adjusted that 20 milligram will be equivalent to 100%. That is considered as 100%. Okay. And then this heating program is been done. And as you keep on heating, like now look at this y-axis, x-axis is a temperature. So there is an increase in temperature 0, 200, 400 up to 1000. It is being mentioned here. So as the temperature increases, so what happens to the weight? So that is what this graph is. So there is a weight loss. So now if this region, this is called plateau. So the plateau means there is no weight loss, and there is a dip here, means there is some weight has been decreased, and there is a plateau again, means during this region 200 to 400 there is no weight loss. The compound is stable at this temperature range, and then so you see all the weight loss has been marked in a red color here. So here is a weight loss, and again slight plateau, and then again a weight loss, and finally you started with 100%, and you end up with a nearly some 30-35%. Okay, so 35% of the material still remains even at 800 or nearly 1000 degrees Celsius. Nothing happens. Means the material is very stable at that composition at that particular higher temperature. So this is what actually TG curve. Now here TG curve. Now there is some complications here. You can see some peaks also. So overlapping in this particular thermogram. Now this is actually called thermogram. And don't get confused. So this is actually DTG plot. Now this is a normal curve, that is a thermogram. But here what is mentioned is a DTG. DTG stands for differential thermogram. Differential thermogram is just a differential graph of a thermogrammetric analysis. Okay, what is differential graph? Differential graph, if you recall, in our laboratory you have done the analysis of potentiometry. I hope all of you have done at least one of the potentiometric titrations. So in that potentiometer titrations, we have asked you to carry out the plot the graph, two graphs. One is a simple graph. In a simple graph, you will get a curve just like this TG. So you'll get the curve like this. Okay, the potential slowly decreases and there is a sudden decrease and then becomes equal, negative and all. And we have asked you to plot a derivative graph. What is the derivative graph there? So the delta E by delta, what is that? Small change in the small change in the potential with respect to the volume. Okay, so that was plotted on the y-axis, and on the x-axis there is a change in the volume from the ml from the burette. So that was the derivative graph. And similarly here, when you take a graph of change in delta W versus delta T with respect to the temperature, so you'll get a derivative graph. What is the use of derivative graph is, now this is the inflection point here. So here actually this is a curve, there is a slope here. At the slope where there is a maximum slope, in the derivative graph you'll get a peak point. Okay, otherwise in the normal graph you'll get this kind of curve. So identify the peak point in this dip is very difficult. But however, if you do the same thing with respect to a derivative graph, you will come to know where exactly the peak is appearing. So that's how derivative graphs are useful. And this DTG is not a different technique. Okay, so TG and DTG are one and the same. But only thing is the final readout procedure is done in a differential thermogrammetry, differential thermal plot. Now where this dip is there, you will have a peak. And here there is a dip and there is again you have a peak. And here is a dip and you will have a peak. So this is how the graph looks like. And common gaseous components originating from the inorganic materials that decompose before the melting point are like water molecule, carbon monoxide, carbon dioxide, sulfur oxides, nitrogen oxides, chlorine, fluorine, methanol. So these are the most common components that are normally decomposed away from a material when on heating. Okay, and some case in solid phase, as I told, solid phase reactions, there is a gaseous weight loss. For example, sodium carbonate plus SiO2 gives sodium silicate, and there's the evolution of carbon dioxide gas. Okay. All right. Now this we discuss further the factors affecting the TG curve. So this is called TG curve or thermogram or TG curve. Okay. So the heating rate is going to affect, and the sample size. Okay, they increase the both of them will increase the temperature at which the sample decomposition occurs. I'll explain you for in a while. And the particle size of a sample, packing, crucible shape, and gas flow rate are also going to affect the progress of a reaction. All right, so now I just have some the slides here, which has been taken from the Vogel's quantitative chemical analysis book. So which is considered as a holy book for the analysis, quantitative analysis. So all the chemists usually analyst usually refers this Vogel's book on both qualitative as well as quantitative analysis, and this is taken from the Vogel's quantitative chemical analysis book. Okay, so I do refer everything here because it involves very good information and quite useful also without any mistakes. Yeah, now here you can see the y-axis weight loss and the temperature. Now what is the example? This is actually TG curve of copper sulfate dot 5H2O. So you may get a question in the examination to explain the thermogram of a copper sulfate dot monohydrate, or you may be asked a question like explain the thermogram of one we have considered earlier, calcium oxalate monohydrate. So what you have to do then, plot a graph just like this. Okay, weight loss versus temperature, and you have to show the corresponding weight losses and the plateau and all with respect to temperature, and then you have to mention the reaction that is happening at particular range of temperatures, and then you have to explain what happens in that range and why do you get weight loss, all these things. So that explanation if you do, so that question will, if you answer like that, then I will get full marks. All right. So I even told that there are different types here in this curve. We need to understand what this curve is. So horizontal portions. Now here is a horizontal portion. You can see horizontal portion. Now this horizontal portion is also called plateau. Plateau. So this indicates the region where there is no weight loss. Means what? The weight loss, percentage weight loss. There is no weight loss here. So from the temperature around 200, 300 to 300 to nearly 800 or 700. So the temperature is increasing, but weight has been remaining constant. There is no weight loss. Okay, it means that material is stable within this range. One can say this material is stable at this particular temperature range. Okay, the thermal stability of a material can be explained, can be considered. So this is what one of the application of TG. Okay, and when you found a dip, means what? The weight of the sample is decreasing in this way. So the percentage weight loss can be told. Okay. So okay, to be note here, you so this graph is different here. You need to be very careful here. Percent, when you have a unit as weight loss, when you have a unit like weight loss, so your y-axis unit go from 0 to 100. Means what? 0 means when there is no weight loss. Okay, 10% means there is a 10% weight loss, 20% weight loss, 30% weight loss, and 100% weight loss. But earlier percentage weight was there. I forgot to mention percentage weight. So instead of weight loss, if you simply take percentage weight, means you have 100% weight of a sample, and 100% has been reduced to 80%, and then 60%, 40%, 0% means when all the compound has been gone away. Okay, so whether you have to be very clear, if you are mentioning weight, percentage weight, then the it should be from 100, from top 100 to then to the ground, to the origin, it has to be 0. But if it is a weight loss, it was from 0 to 100. So 100% weight loss means when there is no compound. So 0% weight loss means when 100% material is there, 100% materials are there. So this is how. Then the curved portion indicates the regions of weight loss. Okay. Now, as I told, the TG curve is a quantitative. So it's quantitative. Calculations on compound stoichiometry can also be done. Okay, at any given temperature. At any given temperature, you can tell about its composition also, because you will come to know what is the exact amount of sample that remains after so constituent has been evolved away. So that's how thermogrammetry is. It is not just a qualitative analysis, but it does the quantitative analysis, because you are going to measure the you are going to measure the weight loss. Everything is under your count. So if there is any weight loss, that count is with you. So it is a quantitative analysis. So here you see the copper sulfate pentahydrate. Okay, so which is being decomposing at a 4 different stages. It is decomposed at a 4 different stages. Okay. So their approximate temperature weight loss range has been given. So it undergoes decomposition at 4 stages. So CaSO4.5H2O undergoes decomposition to give CaSO4.H2O within the range of 90 to 150 degrees Celsius. So most of the water molecules, they'll go out in this range because as you know, the boiling temperature is 100 degree, but still even it goes to the around 200 also, because it is not just like a free water molecule that is there, because this water molecule is trapped in a crystal lattice and it is having some core connectivity with the crystal stuff. So that's how the entire weight loss of all the water molecules to get an anhydrous compound. So it requires little higher temperature. So now this is actually, you can find there is some weight loss here. There's a small curving here. There's a weight loss here. And CSO4 dot monohydrate to give anhydrous copper sulfate. So temperature range is 200 to 275 degrees Celsius. So up to 275 degrees Celsius, say around 275 degrees Celsius here. So all the water molecule, the entire 5 water molecules have been gone away. And after that, there is a very long plateau from up to 700. Look at this, from 275 or nearly 300 to 700. So the material remains as an anhydrous copper sulfate. Okay, so that it clearly indicates, suppose if you heat a material to around 700 degrees Celsius, if you heat a copper sulfate .5 at around 500 degrees Celsius, so then its composition will be anhydrous copper sulfate at that temperature. So the material will be in the form of anhydrous copper sulfate for very sure. Okay, so that because the proof is thermogram. The proof of this statement is thermogram. Means what? Thermogram tells you about the thermal stability of a material over a range of temperature. Okay, so then what happens after 700 degrees Celsius if you heat further? So copper sulfate is not so stable, and at 700 degrees Celsius it starts to decompose to give copper oxide and sulfur dioxide and half O2 molecules. Okay, so it decomposes to cupric oxide. CuO is a cupric oxide because copper is in the 2+ oxidation state, and it gives out sulfur dioxide is gone away, and also half moles of oxygen is been gone away in the range of 700 to 900 degrees Celsius. And further, if you heat to about 1100 degrees Celsius, so two such cupric oxide molecules will combine to give cuprous oxide CO2O, and further there is a liberation of oxygen. So this last final step will complete in the 1100 degrees Celsius. And finally, what that remains is a cuprous oxide that is quite stable. And the final product of that one is this cuprous oxide. Okay. So here, in the beginning, what represents the true weight of the sample, and then the percentage of the total weight. So it also tells about the relative molecular mass units and all. Okay, so now I have shown here is a differential graph. Now here this is the normal graph of the typical TG curve of copper sulfate dot pentahydrate, and here it is the DTG of the same example of copper sulfate dot monohydrate. Okay, however, look at this, there is a decrease, and wherever there is a peak portion of a slope, so you will get a peak at that particular one. So you have this kind of peaks like this in a differential graph. That's dW upon dt with respect to temperature. So this will give some better picture rather than the simple TGA plot. So always the instrument is calibrated in such a way that it can give you both thermogram as well as both TGA as well as the DTG plots. Okay, so that will help you in rightly identifying the this particular graph. Okay, so here that has been explained. If the rate of change of weight with respect to time is plotted against temperature, a derivative thermogram, that DTG is obtained, and this DTG curve, when there is no weight loss, then there is no weight loss, then dW upon dt is 0. Okay, so that value is 0. The peak on the derivative curve correspond to the peak point of the when there is a maximum heat loss. Okay, now the heating rate is having an impact. Okay, now so far I didn't tell the impact of heating rate here. So even I told earlier that heating rate can run from 0 to 50 degrees Celsius per minute. Okay, so you can vary the heat rate. Now, what is the what happens if you change the heating rate of a the heating program, if it involves the different types of heating rate, like sometimes you use a fast heating rate and sometimes you go very slowly. So what is the impact of variation of the heating rate on the thermogram? So that's what been shown here. Now here is a plot here. So sorry, in this plot, what is it shown? Actually, maybe hope this is visible, but the x-axis is not visible. X-axis is nothing but the temperature, and y is the weight here. The weight decreases, of course, like this, and this both are this is a dotted line and this solid line. So both are for a same material, but what is done here is the same sample is put in a different heating programs. In one heating program, there is a slow heating rate is being used. In another case, there is a fast heating rate. So when the heating is done when a fast, so then actually the same weight loss will begins at a higher temperature. If you do if the heating rate is fast, like instead of doing the heating rate as 10 degrees Celsius per minute, if you do 100 degrees Celsius per minute, then the for the same material, okay, if the for 10 degrees Celsius per minute, if the weight loss starts at A, and if you do it for a 100 degrees Celsius per minute, so then for the same material, the weight loss begins at C. It takes at a higher temperature. Temperature in the y-axis, sorry, the x-axis, there is a increasing in the temperature. So this is quite sure. And same thing, you can see do some equation here like TA. TA and TC are the temperatures of the beginning of the decomposition here. So this TA and this TC means temperature at TA, temperature at C. Now this quite sure TA is less than TC, and now this is a TB when the weight loss is complete, and this is the weight loss is complete at this one. TB is less than TD. But similarly, you can prove that then TB minus TA, TB minus TA is less than TD minus TC. What does this mean? It means if you choose to have a faster heating rate, then this is the sudden drop actually in the weight loss cannot be shown. However, it goes as just like a flat. Okay, so you don't have a sharp weight loss. Sharp weight loss is not been there. So however, there is a you can see a continuous weight loss. So the good feature of the thermogram is been lost if you go for a faster heating rate. So therefore, as far as possible, a slow heating rate is been preferred over a fast heating rate. Okay. And also there is something called as a dynamic heating rate. If an instrument is capable of dynamic heating rate, so that is also being used. So what is the means by dynamic heating rate? Like for example, if you want to study the decomposition of copper sulfate monohydrate, then if you have put a heating rate for an instrument like a 5 degrees Celsius per minute, so then you will get a very good curve, very good decomposition plot thermogram. But however, you have to wait for a long time to go from the temperature from 200 to 700 degrees Celsius. So this period, okay, so this period will you have to wait for a long time. So if it is a dynamic one, then what you can do is, if you know the curve here, if you have taken a curve initially, so wherever there is a curve that you are obtaining, you just make it slow. You can put the slow heating rate, and whenever there is a plateau region, then you can increase the heat rate. The heating rate can be increased so that you can reach up to this stage quite fast, and then you make it slow heating rate. So this is called dynamic heating rate, and that is actually better one. so that you can save some save the time of analysis. Now, what I'm now speaking is the factors affecting the thermogram. So one thing, the factor affecting thermogram is a heating rate. The next one is a furnace atmosphere. So furnace atmosphere is again another thing that is going to affect the the heating rate. Okay, I hope you please do hold on. So in about further 20 minutes, I'm going to complete this class, and I'm going to complete this talk on the thermogrammetric analysis. Hope you are there with me. Okay, so furnace atmosphere means in the furnace, if the atmosphere, the different furnace atmosphere will have an impact on the this thermal studies. Suppose if you are studying the decomposition of a calcium carbonate, okay, calcium carbonate decomposition in one of its step, it involves the decomposition product as a carbon dioxide gas. And if the atmosphere also, if it is carbon dioxide, okay, if you put an atmosphere of carbon dioxide, then what happens? So then the decomposition occurs at a much higher temperature. Okay, if you have put the atmosphere as carbon dioxide and the gas that is going to liberate it is also carbon dioxide, so there is a reversible pressure on the material, so that the decomposition occurs at much higher temperature than expected. So it means to say that the furnace atmosphere, the inner atmosphere, the ambience of a furnace is have an impact on the thermogram, on the temperature at which the weight loss begins. So that is that depends on the furnace atmosphere also. But instead, if you take a nitrogen as an nitrogen atmosphere, nitrogen is a neutral. It won't have an impact on anything. It won't come to any chemical reactions. Many times, either nitrogen atmosphere or argon atmosphere is being used. So just like a neutral atmosphere, that won't take part in any reaction. In some case, the simple oxygen is used, and you can see those things as a static air, dynamic air, and nitrogen gas atmosphere. And in some case, you study the heating is done with the in vacuum. In vacuum means almost a vacuum. Means what whatever the gas that liberated, it is suddenly been sucked away. So when that is been done, the heating or the weight loss will occur very comfortably, so that you will get a good sharp weight loss and all. Okay, so there are three different atmospheres that are commonly used in TG. There's a static air. Static air means air from the surrounding flows through the furnace temperature. Nothing is been done. Just the furnace is just open. So you are simply heating the program and just recording the temperature as well as the weight loss. So there is a normal flow of the atmosphere. So that is called static air. Okay, so it depends. Okay, whereas dynamic air furnace atmosphere means a compressed air from a cylinder is passed through the furnace at a measured flow rate. Means what? You are supplying the air. So air is being made to flow from a compressor instrument. A compressor, air compressor is being taken, and compressor is made to flow. That is made to flow from one area to another area inside the furnace. There is an inlet and outlet in a closed atmosphere. So that is called as a dynamic air. And sometimes you need to have a oxygen-free atmosphere, because oxygen will take part in any reaction. If you want to take out oxygen, and if you want to do the heating program in a neutral atmosphere, then you have to take it should be purged in the nitrogen gas. Okay. Sometimes the atmosphere take part in the reaction also. The humidified air have been used to study the decomposition atmosphere of hydrated metal salts. Okay, so that is done. Okay, so thermogrammetry is a dynamic technique. The convection current arising in a furnace will cause a continuous change in the gas atmosphere. Okay, so gas atmosphere will change because there is a different gaseous materials that have been liberated. So one needs to take care of the suitable furnace atmosphere. We have seen initially the heating program and then the furnace atmosphere. The next one is the crucible geometry. How the crucible should be. What is the better geometry of a crucible? That is also going to have an impact. If the crucible is like a cone shaped, okay, and if a crucible is a flat, so then there are two things that is going to have an impact on the thermogram. If the crucible is in the cone shape, of the less space, then you have to pack the materials and the sample. And in such case, what happens? The gas that is decomposed, any gas that is leaving out, so cannot leave out properly or slow easily. So that is going to certainly have to impact on your impact on the alter the slope of the thermogrametric curve. Okay. However, if you have a flat plate shaped crucible, that is generally actually that is preferred than the cone shaped one, because if you have a flat the plate on which if the sample is spread, even the sample should not be put as a heap, it should be spread as a thin layer. So then what happens, any gas or any decomposition will be clearly given, and you will have a better thermogram. So the crucible geometry is also going to have an impact. And then sample characteristics, okay, is also important, which affect the thermogrametric curve. So the particle size and its mode of preparation, that means the prehistory of the sample, so they are also going to have an impact. Okay, if you have a large sample, so then that is going to have a deviation from the linearity in the temperature rise. If you have a large sample, because if you put a bulk of the sample, what happens? Some of the sample receive the heat, and some top portion may not receive the exact temperature that the thermogram is have been reached. So there will be gradation. There will be gradation in the temperature that is being felt by the sample portion. So that's how, as far as possible, sample size should be small, and even the particle size should also be small. If you have a the granules like samples, then you will not have a good decomposition curve. Okay, so any gas that have been evolved should be effectively evolved and should be taken away. If the sample is just like a lumps, okay, so then the complete evolution of the gas will happen at a very slow rate, and you will not have a very sharp weight loss. So which will certainly mislead you to be a plateau. It won't be a plateau, but there is a slow decrease. So you will not have a good grip over what is happening in that particular stage if you are using a sample in the form of a lumps. So that's how the sample that is used in TG should be in a fine powdered state, and yeah, as far as possible, take a minimum sample size and spread it over on the pan of the sample holder, so that you will have a good thermogram, and or the thermogram can have a good information. Many times, depending on the sample, sometimes the sample undergo decrypitation. So if you have it is having a metallic nitrates, so decrypitation will happen like spitting and spattering. So hope you know the term decrypitation. And sometimes a sample may swell and foam may happen, even bubbles might come out. So these are certain problems that we encounter with the different types of samples. Okay, then the instruments that are used in thermogrammetry. So a good thermal balance design. So thermobalance should be capable of continuously registering the weight change of the sample studied as a function of temperature and time. Okay, so in time is there. Sometimes it is measured with respect to time also. Time and temperature. Okay, so the thermobalance should be a good one, which is having a capacity to continuously measure this weight loss or weight gain. So the furnace should reach the maximum desired temperature. So see, with some modern thermobalance, the temperature range goes like -152 to 4,400 degrees Celsius. So it should be capable of reaching that, not just that is mentioned, it should be capable of reaching the high temperature. So the rate of heating is linear and reproducible. So they should choose such a heating rate that the heating is done so that you'll get a linear and should be thermogram should be reproducible. That means if you do it again, you should get a similar or the similar curves or a similar plot. If there is a if precision is not there, then you're not sure about this analysis. Okay, so this is something about sample holder and all, and then the thermobalance should have a facility for provision for variable heating rates. Okay, that means various heating program should be able to set by the analyst. So that arrangement should be there in the this thermobalance. Okay, so that it is to permit the heating in a variety of controlled atmosphere, and for the heating in vacuum, that is in vacuum also, that should also be made possible in the instrument. And the instrument should also be capable of carrying out the accurate isothermal studies. Okay, so at a constant temperature, so what will happen with the weight? So that also should be possible. Okay, if you want to stop at particular temperature, so that also should be possible. The provision should also be made with the furnace. So balance mechanism should be protected from the furnace and from the effect of corrosive gases. So because you are continuously measuring the weight of the sample, and remember, so in any chemistry laboratory, the balance room is kept away from the laboratory. Okay, so you have seen in our department also. So there is a separate room called balance room, wherein actually the balance, chemical balance, and the digital balance, everything has been kept. Because usually balance should be kept in an ideal condition where they should be away from the hazardous chemicals and chemical vapors. Otherwise, they're going to harm the pans and all. So, but however, here everything is assembled in one particular instrument. That's what care should be taken, that it should be the balance, the weighing mechanism should be protected from the furnace at the heat. It should not be affected by the heat, and also it should not affect the affected by the corrosive gases. The temperature of the sample must be measured as accurately as possible, and a balance sensitivity should be suitable for studying the small sample weights. Okay, it should be a very sensitive thermobalance. Balance should be highly sensitive one, because we operate in the range of few milligrams, and if there is any small variation in the sample weight, then that should be rightly recorded. Your balance should give a response to the weight loss or weight gain. Okay, and there are some extra things that can be associated in a modern balances. Facility for rapid heating and rapid cooling in a thermobalance should be made available or should be there. So this permits the several analysis to be carried out in a relatively short period of time. That means you should be able to increase or decrease the heating rate. The instrument should be capable of plotting a DTG curve, because DTG curve really help you know about the exact temperature at which there is a maximum weight loss. So that can be measured if you have a plot of DTG. Make sure there is a straightforward coupling with a gas analyzer. Okay, that's for EGA analysis. Okay, EGA analysis means evolved gas analysis. If there is any gas evolved, so that if it is directly connected to mass spectrometer, you can determine the mass of the substance that is coming out. Or if you gas that is dissolved, evolved, that can be analyzed to GCR, this is a gas chromatography. So if that is connected with another instrument, another such instrument, then you can have there's an added advantage, like you can connect it to mass spectrometer, connected to a chromatography, or it can be connected to FTIR, means infrared spectroscopy. You don't know about these things, but we will gradually know about these things shortly. Okay. A dynamic heating rate, as I told already, allows the high heating rates in regions where there are no weight changes. As I said, if there is a plateau, if you know, then you can increase the heat rate. Okay, but it can be continuously varied in response to the decomposition rate of the sample. Now this is what I already shown, and now I think we are moving towards the application, the final part of this thermogrammetric analysis. Again, this is a simple graph of weight percentage. Look at this. If it is a weight percentage, then the graph will be 100, 90, 20, like that. You can stop at 60 or you can go below also. It depends. Okay, and this is the temperature. So this is actually done for some hydrogen carbonate mixtures. All right, now let us focus on the very interesting aspect of thermogrammetric analysis, that is the applications of thermogrammetric analysis. Okay. So there are 4 different areas or the main applications of TG wherein this been used. Okay. So determining the purity and thermal stability of both primary and secondary standard materials. What do you mean by this? It means in a titrimetry, okay, in titrimetric analysis, you have studied something called primary standard compounds and secondary standard compounds. Okay. Sorry. So this means you can determine the purity. See, a primary standard compound is the one which should be available in the highest purity, because the entire titrimetry depends on the purity of the primary standard compound. Because based on that, we are going to standardize the secondary standard compound or solution, and then that is used as an analyst as the standard solution in analyzing the analytes. So that's how all the entire analysis relies on the purity of the material, the standard material that you are using. So how to check the purity of the substance? So that can be checked by thermogrammetric analysis. You study the this primary standard compound, you put it in the thermal studies, and you look at it's a TG pattern, and that will and compare it to the standard another standard compound. So by knowing that, you can see whether the material is pure or not. So purity can be checked, like, see, if you have a thermogram of a material, if the material is 100% pure or 99.99% pure, then you keep it as a standard, and then you take the TG of the material that you are using, okay, and compare it with the standard, and if they exactly match, then that indicates the compound that you have prepared is as pure as what you have in the with the standard. So thereby, or if you find any extra weight loss or extra weight gain, that indicates so this material is occluded with some of the impurities. Okay, so it is one of the use of the TG, that is in the determining the purity of the material of the primary standards and secondary standards in titrimetry. Okay, then investigating the correct drying temperatures and the stability of various weighing forms of the gravimetric analysis. Okay, so this I tell you, you have done gravimetry as I told. Okay, so you have done the gravimetry. Actually, you have done only 3 gravimetric experiments, but there are several types of gravimetry. Of majority of the metals can also be studied based on the gravimetric analysis. So in gravimetric analysis, for barium, for iron and aluminum, what you have done is simply just heated it, charred it, and burned them, and then you took a weight. Okay, but in majority of the other types, the sample is filtered in something called as Gooch crucible. Gooch crucible is the one just like a glass crucible. Okay, so which is used in filtering itself. Okay, there will be in the just like a glass cup. Okay, one glass beaker at the bottom, instead of the glass wall, so there will be some silica gel, which is a porous silica bed will be there. So which is porous enough to pass through the water or a liquid, but however it will stop hold the sample material. So usually in some grammatory like nickel DMG grammatory. So nickel is precipitated as nickel DMG and then filtered in a gauge crucible. So you have to collect that precipitate in a gauge crucible and then you have to heat it in a oven or a furnace until you get a constant temperature. So if you know the TG of that one, then the TG thermogram of a standard material that will give you a guidance as to where to stop or at what temperature I need to heat this sample and then take the weight in order to have a known composition of the material. So that's how it is used in the investigating the correct drying temperature and stability of various weighing forms of the gravimetric analysis. Okay. So like if you finally weigh the sample of iron gravimetry, what you have precipitated as ferric hydroxide, but on charring and then on decomposition and further heating in what is this heating in a crucible, you will end up it as a Fe2O3. So that is the composition of Fe of ferric hydroxide is on heating further everything get converted to ferric oxide. Okay. Now that is actually the weighing form of a weighing form that is meant by weighing form. And if you are doing barium gravimetry, it is weighing form is barium sulfate only. If you are using aluminum, the weighing form is Al2O3. So determining the suitable weighing form is also possible by TG and direct application to various analytical problems. And there are determining the composition of alloys and mixtures. You have an alloy, you put it in a thermal studies, and you come to know about the its composition. So that is also possible. So you can do the see the analytical reagents like in titrometric analysis like primary standard sodium carbonate, sodium tetracarbonate, potassium hydrogen phthalate. So they can be measured. They can be their purity can be checked with the TG analysis. Okay. So you can check about the purity of the primary standard. Sometimes they absorb certain amount of water and moisture from the atmosphere. So TG tells you how to keep this material stable so that you can put it in a oven at certain temperature so as to keep keep it as a pure one. So purity is not a big deal in your analysis, but however, it does matter when you are when you are an analyst in a company because the result that you are produced should be comparable uh, with accuracy. So that is only possible when you are using a pure 100% pure materials. So it can be determined by this TG. Okay. So and also TG before I don't read everything, but I just have put this. In case of pharmaceutical products, TG is used to determine the shelf life of tablets. Okay, how do you do that? So you all have seen every tablet, pharmaceutical medicine. So we'll have a label and on the label batch number, batch production, everything will be there. And in various you can also find something called the expiry date. So how the expiry date of a tablet is being done? So that is the interesting thing that the question might have come to your mind. So because expiry date will be sometimes 3 years, 4 years, then does the analyst, if he is preparing a chemical compound or a pharmaceutical of a chemical compound of pharmaceutical interest, then does he wait for 4 years and assess its stability till 4 years, or else how does he do it? Remember, nobody waits for 4 years of the material to check the stability of a material, but instead it is studied in a higher temperature and then made it equivalent to the current one. It means what? if you have a prepared as a tablet or a particular composition, so the TG of that one is studied, and it is increased to a certain temperature, and then material stability is checked. Okay, so and that is actually calibrated. If the material is stable at a certain temperature, certain higher temperature for a certain period of time, that is equivalent to certain year. So that equivalent or the standardization is usually done, and then based on that material stability in the thermogrametric curve, so its expiry date can be evaluated. So this is one of the very interesting application of TG in the pharmaceutical analysis. Okay, and also here what is mentioned in this paragraph, a scientist called Duval, Duval. So what he did was he studied the gravimetric precipitates of nearly 1,000 the metal compounds, or a same metal compound. He took a various organic compounds and studied them, precipitated them, and then their gravimetry has been studied. And so how could he ascertain the right heating temperature of a gravimetric sample? Is the Duval studied the thermogrammetry of those materials, and based on that thermogrammetric curve, he decided the heating temperature or the temperature at which the material is stable, how long you can keep it in a stable composition at a range of temperature. So that procedure has been developed by the scientist Duval for various metal salts. So all these iron, barium, aluminum, the the gravimetric experiment what you are doing in our lab. So it was initially done by these scientists, and he has been standardized the procedures. Okay, so with the help of thermogrammetric curve. So that is what the interesting application of this TG. And TG also helps in the analysis of a mixture. Okay, so now suppose you have here is a the TG data of a calcium oxalate, which we have seen earlier, but the data is also here. So the automatic determination of a mixture of calcium and magnesium as their oxalates. Calcium oxalate monohydrate has three distinct reasons of decomposition, whereas magnesium oxide oxalate, magnesium oxalate dihydrate has only two distinct TG plots. Now you see calcium oxalate monohydrate, so gives anhydrous one. Okay, anhydrous, and there is a liberation of water occurring at 100 to 250 degrees Celsius. And here is a anhydrous calcium anhydrous calcium oxalate, which gives you calcium carbonate and carbon monoxide. It happens around 400 to 500 degrees Celsius. And finally, calcium carbonate decomposed to calcium oxide and carbon dioxide up to 850 degrees Celsius. This is what the TG pattern of calcium oxalate monohydrate is. So you should be able to write this one, practice this, and by heart this one if it has been asked in examination. And if you take the TG of magnesium oxalate dihydrate, so both the water molecules will be liberated in this temperature 100 to 250, which is same as here. And you have a magnesium oxalate anhydrous, so it decomposes directly without coming to carbonate stage. It will directly decompose to magnesium oxide and these things, and it happens around 400 to 500 degree Celsius. And even suppose if you have a mixture also, so one can determine the presence of magnesium oxalate as well as the calcium oxalate. A pyrolysis curve for a mixture of these two oxalates would thus show three decomposition steps. The final step would be due to entirely to the loss of carbon dioxide from the calcium carbonate. So if you have a mixture of calcium oxalate and magnesium oxalate, so for 100 to 250 Celsius, this as well as this will liberate away the water molecules, will get anhydrous. One second. Okay. So if you have this magnesium, both of them, these are the same peak will be for the decomposition of water. And even for this one, there is a decomposition for calcium carbonate, and this decomposition both will happen at 400 to 500 degrees Celsius. But there is a distinct peak only for the decomposition of calcium carbonate here. So you will be having the percentage weight and everything. So with this, one can also determine the amount of calcium oxalate as well as magnesium oxalate that is present. I think last but not the least, again, these are the two slides I'm ending, concluding this one. So this is actually a thermogrammetric analysis of some polymers. See, the TG is finds application in pharmaceuticals. Sorry, the pharmaceuticals as polymer industries. So because if you want to study the thermal stability of a polymer material, so that is well studied in the thermogrammetric analysis. Okay, so you can see the weight loss and you have the temperature. So you have you see the various materials like 1, 2, 3, 4. What are 1, 2, 3? PVC, polymethyl methacrylate, and low density polyethylene, and polyterfluoroethylene. So these are the four polymers and their TG plot. Okay, so the first one, PVC, will have a weight loss at this temperature and then plateau, and further they'll decompose away. And however, so you have this one PMMA and this LDPE and all these things. So the material stability is made to known, and what is the polymer content, that is also made to known. Okay, so you'll come to know about various thermal properties of these polymers. And finally, so you can have this proximate analysis of coal, or the coal is a fuel. Coal is a fuel. This is the last slide. I'm just winding up. Don't worry. So this, if you want to study the fuel content of a coal, suppose if you the coal mining unit is there, and if you are extracting coal, and if you want to study whether this coal is having a good fuel content or not, so then it is being studied. Just a minute, once. Okay, so the weight loss with respect to time is been done for this coal, and which will tell you the characteristic of this, the quality of the coal can be studied. Look at this. What is happening now? This is a teaching curve. So this is the weight loss now, 100% sample. Okay, 100% means there is no weight loss. And as you keep on heating, like now it is shown here, 25 to ambience temperature, 25 to 120 degrees Celsius. So what is happening? There is a slow decreasing the weight. What is it? What it shows? It shows moisture loss. Okay, so there is a moisture loss. Now, okay, and at the same time, there is a loss in some weight. Okay, now this loss in weight is due to some volatile matters, volatile organic matters that is decomposed. Okay, so the moisture loss is shown here. And further, there is some stability. So the dry coal will go up to some temperature around, I think, I don't know. The temperature scale is not clearly given here. Okay, so from 120 to 950 degrees Celsius, it is been entirely taken, and it is studied in the atmosphere of nitrogen. So in the nitrogen atmosphere, it is done for a dry sample. And look at this, and the furnace atmosphere is changed to oxygen here, Len. Because if you want to study the fuel content of coal, then you have to change the furnace atmosphere to oxygen, because in the nitrogen atmosphere coal cannot burn, because if you want to burn the coal you need to have oxygen. Okay, but however, when you do it in a nitrogen atmosphere, you can study the moisture loss and volatile organic matter. So finally, when you change the furnace atmosphere as oxygen, then the coal will burn, and all the fuel content, hydrocarbon content in the coal will combust away, and all of them will be lost as a carbon dioxide and water molecules that is driven away. So, because you are maintaining the furnace atmosphere as oxygen, because oxygen atmosphere is required for burning process, for the combustion process, and all this coal is burnt away, and finally it is again changed to nitrogen when all the fuel content has gone. So it is again stored in this little nitrogen atmosphere. Okay, so what finally that remains, okay, near to the zero, not exactly zero, it is actually ash. Okay, now what is the use of this analysis of coal in thermogrametric? That is, what all things you come to know. So you come to know what is the moisture content of the coal. Okay, if the coal is having a very heavily moisture content, because if the decrease is very, you find a lot of dip here. That indicates the coal is not very good for heating purpose, or in order to catch fire the coal, then you have to the preheating requirement is more if the moisture content is more. So that will that you can decide how much temperature or heat is to be supplied to the coal to have a to make it catch fire. So that decision can be done by looking at STG, one thing, and what are the amount of volatile unwanted material that is there in the coal. So the percentage weight of that much of moisture and volatile matter can directly come to know by the TG plot. And finally, you will come to know what is the fuel value, the exact fuel content, the in terms of weight of percentage weight is a very good information you are going to get about the fuel material. So what is the fuel content of that particular coal can be directly obtained from the TG plot. And finally, what is the ash content? How much ash that you are producing if you use that particular sample of coal. So that it also gives you the ash percentage ash that remains, because you never reach the zero. You'll end up with some metal oxides which will be very stable at even 1000 or 2000 degrees Celsius. So that is actually the ash content. So entirely, finally, what this analysis helps you is in determining the fuel quality of a coal or different fuels, their fuel efficiency can be studied by using the thermogrametric analysis. So thermogrametric analysis. So I think I stop at this stage because so further in this there is a DTA and all this there. So DTA is not mentioned in your syllabus, and hence I am just I'm not going with that one. Just a minute, and don't go away. I even would like to take your attendance. Okay. I can see some 50+ students here. I hope so far you could be able to see my screen, and I could everything was fine with the concept and all. So if there are any questions, feel free to ask me. To sum up, I can just tell you, thermogrametric analysis is one of the method of thermal analysis. So there are varieties of techniques in the head under the broader head of thermal analysis. So thermogrametric analysis, one among them. So your syllabus comprises only thermogrametric analysis, and then just I confined it with this one. So thermogrametric analysis can achieve both qualitative and some quantitative analysis, which can make the study of compositional analysis. Okay, so what is required here in the instrumentation is you have a thermal balance and you have a furnace and all. Okay, so and the instrumentation setup, the requirements are you have to focus on heating rate, you have to look at the crucible geometry, you have to look at the what is that? The sample type, and you have to look at the furnace atmosphere, whether the nitrogen, carbon dioxide, oxygen, air. Look at that in final example. So at the determination of weight, moisture, and volatile organic material, you have to look at the nitrogen atmosphere, and if you want to study the fuel value, you change it to oxygen atmosphere. So like that, furnace atmosphere will have an impact, and you have seen the thermal decomposition, thermal studies of copper sulfate dot pentahydrate, and you see the thermal decomposition of calcium oxalate dot monohydrate. Okay, so these two things are also important, and the application of TG in determining the thermal stability of a material, in determining the expiry date of a medicine, in determining the purity of a primary standard compounds in a titrimetric analysis, and in determining the fuel analysis, fuel characteristic of a material, fuels. So these are the different applications, and also determining the suitable heating temperature of a gravimetric precipitates. So these are the varied applications of thermal analysis, and also it is having application in pharmaceutical industries to identify the various polymers. Okay, so that's all from me on this particular topic of TG. And if you have any doubt, feel free to ask. So if not, just wait for a second. I'm just going to download your attendance. And maybe from the next Monday and Tuesday, I do have a class. And in the class, I am going to begin with the chromatography. Okay, so I am going to discuss with the what that remains in my syllabus is chromatography, and then the solvent extraction. So these are the two titles that remains in my syllabus. So which I do take up in a regular class, as well as I take some special class in the mornings. So that I decide in Monday and Tuesday class, I decide the time of some special class so that I complete your syllabus in a matter of 1 or 2 weeks. Okay, in the next week or within the 2 weeks. So I have a plan to complete your syllabus, and all these materials will be provided to you. Okay, so both the slides as well as some reading material from the quantitative or Vogel's quantitative book. I am going to give you the study material. So I even have downloaded your attendance. Is there any doubt? Or can I have one final feedback that everything was audible and everything was okay? The slides were seen properly so far? Yes or no?
Yes, sir.
Okay, thank you. So if there are no doubts, you can just you can leave the class. Thank you. Or if any questions, you can ask. Okay, then thank you. Bye.